This is video 2 of our chapter 10 test review. And here we have a fun question, and we have a pure gas, a sample of a pure gaseous hydrocarbon. Hydrocarbon, remember, means you have an H and a C, some sort of fuel. So these can be different numbers. Usually this is written as CH, like CH4 or something, C2H6, something like that. Is introduced in a previously evacuated rigid 1 liter container. So we have a container. The pressure of the gas is 0.200 atmospheres at a temperature of 127 Celsius. Okay, so we've got some ideas. All we have in this container now, we'll say it's kind of like a bulb type container. All we have is this hydrocarbon, this one substance in here. They want us to know the moles. Well, they've given us all the parameters for PV and RT. Why don't we solve for moles? And moles is PV over RT. In this case, the pressure is 0.200 atmospheres. The volume is given us 1 liter, makes it easy. R is still a constant, 0.821. And our temperature is 127 plus 273. That should give us exactly 400 Kelvin. So if you go ahead and plug these numbers in, you should find yourself 0.00609 moles. Now when you're doing these calculations, be careful to make sure you divide properly. Some students will do this times this, divided by this, times this, whereas you have to divide by this number as well. So just make sure you get yourself this amount. Okay, that wasn't too bad, pretty easy. We've done this plenty of times. Part B says O2 is introduced into the same vessel containing the hydrocarbon. So we're going to put a little bit of oxygen gas into this vessel. And we're probably going to undergo a combustion reaction, always fun. After the addition of the oxygen, the total pressure of the in the vessel is 1.40 atmospheres at the same temperature. Calculate the partial pressure of O2 in the vessel. So this is actually a very simple calculation. What we're saying is that the individual pressures now combine to give you the total pressure. And if you want to know the individual pressures, just take the total minus one of the pressures and you'll get the other pressure. And that's exactly what we'll do. So to get the pressure of O2, we get ourselves 1.40, which is the total pressure, minus the 0.200 of the hydrocarbon, which gives us 1.20 atm of oxygen. So also pretty simple. This is just a quick partial pressure calculation. Now where it gets exciting is in part C. So why don't we scroll up a bit and see whether we could make sense of part C here. Okay, the mixture of the hydrocarbon and oxygen is sparked so that a complete combustion reaction occurs, producing carbon dioxide and H2O, the products of a combustion reaction. The partial pressures of these gases are 0.600 and 0.800 for water. So 0.6 for CO2, 0.8 for water. There is still some O2 remaining in the container at the end of the reaction. So they want us to use the partial pressures of the CO2 and H2O, the new information they gave us, to calculate the partial pressure of O2 consumed. Now the idea here is we can use pressures just like we use moles in a stoichiometry problem, just like the previous example that we saw. So let's go ahead and write our reaction. And instead of using moles, we're allowed to use pressures because moles and pressures are directly related. So we have a hydrocarbon, some CH compound, reacting with oxygen, producing CO2 and H2O. Now at first glance, it seems like they're telling us the partial pressures. So we could put 0.600 in front of here and 0.800 in front of here, and then just balance the equation. So actually that's what we want to do here. So for the sake of ease, I'll go ahead and put a 6 in front of here and an 8 in front of here. We'll assume it's 0.6 and 0.8, but it'll be easier to balance the 6 and the 8, and then we'll add the point later. So if you've got this equation, the oxygen, to balance the oxygen, here we have 6 times 2, we have 12 oxygens. Here we have 8 more, that's 20 oxygens on the right side. So we need a 10 in front of here to make it 20 oxygens. Now because this is really 0.8 and this is really 0.6, this actually is 1.0. Not 0.0 because it's 10 less essentially. for each one of them. There's a little trick. I mean, you could have balanced it with the 0.6 just as easily, but hopefully that works. Apologize. Okay, so the answer is right there. 1.0 for the atmospheres. 1.0 ATM of O2 consumed. So again, this is actually, it seemed simpler than it was, but coming at this question without knowing this, you may have had to scratch your head for a few hours. So part D says, on the basis of your answer above, write the balanced chemical equation for the combustion reaction and determine the formula of the hydrocarbon. Look at that, we've almost done it. In fact, what's left is just to do something with this guy, with the hydrocarbon. Now that's going to be a bit tricky. So let's just rewrite it. So we have CH plus O2, giving us CO2 and H2O. And because this has been already done, so we'll put a 8 in front of here, a 6 in front of here, a 10 in front of here. Here we're just using the balanced equation. Now the question is, what do we put in front of here? Now it turns out the formula of the hydrocarbon, the C and the H, is where these coefficients came from. So in fact, we used to have 6 carbons, we used to have 8 hydrogens. So we could think of it like this, 6 carbons and 8 hydrogens. And that would give us the empirical formula. However, it could have been a little different. We could have actually had 2 C3H4s. This would have worked just as well, correct? Yes, it would have, because we'd have still gotten 6 carbons, just like we need, and 8 hydrogens, just like we need. So which one is it? Well, if we take a look at part A, if we scroll up and take a look at part A, in part A, it says that our hydrocarbon had a pressure of 0.200 atm. And this gives us the clue. In fact, if this is 0.6, this then would have been 0.2, which means if we drop them, this is a 2 to 6 ratio. This is a 2 and this is a 6. So if this is a 6, in fact, we would make this into a 2. So what we're saying is that the 0.200 atmospheres proves that it's this scenario and not this scenario. So this is actually wrong, and the balanced equation is actually this one here. Again, that was a bit interesting if you don't agree. Incidentally, for those of you that are interested, C6H8, I'm sorry, C6H, not H8. It would have been C6, wait a minute. A little boo-boo. Come back, not C6H8. We have 6 carbons, we have 16 hydrogens, do we not? I apologize. This should have been a 16, which means this should have been the 8. So we found a little mistake. And but the logic still carries over. I just said 8 instead of 16. And what I was going to show you is that this compound right here does not exist. C6H16 does not exist. If you've taken organic chem, or if you want to take organic chem, you'll see that this is incorrect. So, but this definitely does exist. So this exists, it's a real compound. This does not exist, it's not a real compound. Okay, either way though, that is the answer. Last portion, part E, says calculate the mass of the hydrocarbon that was combusted. So, we know the formula of the hydrocarbon, C3H8. Here's our formula, C3H8. We need to know the mass. Well, we know the moles. We actually calculated the moles in part A. From part A, we had 0.00609 moles, and a mole of C3H8. Incidentally, this substance right here is propane. If you calculate the molar mass, you got 3 carbons, each is 12, that gives you 36 roughly, and then 8 more hydrogens, that gives you roughly 44, 4411 to be exact. And if you multiply these two numbers, you should get yourself 0.269 grams of your hydrocarbon. And that does it. So the interesting portion of the problem was C and D, very interesting. So think through it, maybe get a blank sheet and retry this. But this is indeed a very, I would say, very difficult AP exam question. It's one of those that is simple to calculate. The calculations are actually not that difficult. The concept behind to get you there is the difficult part. So hopefully you've enjoyed this and be prepared for the test over Chapter 10.